So my name is Gil Ben-Shachar, and I'm going to talk about the joint work with Gil Barequet, my advisor, on minimal parameter lattice animals. So I'll start by defining what lattice animals are. So a lattice animal is just a collection of connected cells on some lattice. For example, on the square lattice, we have this lattice animal, for example. On the square lattice, we'll call it polyominoes. And through all this presentation, gray cells will represent lattice animals, and white cells will represent the perimeter of the lattice animal, which is the cells adjacent to cells of the lattice animal. And we have other lattices, for example, polyhexes on the hexagonal grid, polyamounts on the triangular grid, and polycubes on the cubical grid. And I'll go start by some definitions that we'll all know everything. So a lattice animal I will denote by Q, and the area of the lattice animal, which is the absolute value of Q, is the number of cells it is composed of. The perimeter, as I said, is the set of cells adjacent to the lattice animal. We will denote it by P of Q. And lastly, the border of a lattice animal is the set of cells which belong to the lattice animal and adjacent to a perimeter cell. So in this example, these are all the cells with X's on them. And I've said that I talked about minimal perimeter lattice animals. So a minimal perimeter lattice animal is a lattice animal which have the minimal perimeter from all lattice animals with the same size. So we fix a given size, look over all the lattice animals, and take those who have the minimal perimeter of this size. And you can see an examples of minimal perimeter lattice animals on all the lattices that I've talked about. Okay, so why did we look on minimal perimeter lattice animals? So it all began with this graph, which shows how many lattice animals are there for a given area and perimeter. Each curve is a given area. Okay, so these are all area 26. And you can see that they distribute pretty well, pretty normally. And in previous work, Asinovsky, Barequet, and Zhang looked at polyominoes with close to the maximum perimeter possible. Each of these curves represent polyominoes with a specific defect from the maximal perimeter possible. So if they looked at the maximal perimeter possible, we wanted to look at the minimal perimeter possible, but in the case of minimal perimeter, this doesn't behave that well. You can see in here. So it is not a smooth curve, it is not a smooth graph. But what can we say about minimal perimeter lattice animals? So if we look closely at minimal perimeter lattice animals, I'll take, for example, minimal perimeter lattice animals of size 7. You can see it in here. M7 is the set of all minimal perimeter lattice animals, lattice polyominoes of size 7 in this case. You can see that we have only 4. And of size 17, we also have only 4, exactly 4. And of size 31, we also have exactly 4. And on top of this, they all look kind of the same. They have this general same shape. And we wanted to formalize it and see what can we say about it. So I'll start by 2 definitions to formalize this phenomenon. So if we have a polyomino Q, the inflated version of this polyomino is the polyomino and the perimeter combined. So this is the inflated version. We added the red cells. And if we have an inflated version, we'll also have a deflated version. And the deflated version is just the polyomino with the border cells removed from it. And this is the 2 definitions that I needed. And formally, we have shown in a previous paper that for polyominoes, if we take a set of minimal perimeter polyominoes and inflate them, we get all the minimal perimeter polyominoes of some larger size. In the case of 7, we get all the minimal perimeter polyominoes of size 17. And then if we inflate it again, we get 31 and so on. And we can keep inflate and inflate and inflate. And in this chain of polyominoes, we will always get sets of size 4. For example, we know that for this 2 million and something, there are only 4 minimal perimeter polyominoes. But this is an old result. And now I'm going to take a break from polyominoes and talk a little bit about chemistry. So I'll define what a benzenoid hydrocarbon is. A benzenoid hydrocarbon is a molecule which have benzene rings. Benzene rings are sets of 6 carbon atoms, and these benzene rings are combined, and around it they have hydrogen atoms. Now you can see that these molecules really resemble polyhexes, so I'll use polyhexes to denote them. And one challenge about benzenoid hydrocarbons is to count how many isomers are there given a molecular formula. What do I mean by that? Given a set of carbon atoms and hydrogen atoms, in how many ways can I arrange them to get different molecules? So in the case of C22H12, for example, we have 3 isomers. These are all the ways to arrange these atoms. And the chemists, they knew, beginning from the 1990s, that there is a phenomenon, but they couldn't prove it, that if we take all the isomers of some certain molecular formulas, for example, C22H12, and they called it circumscribe it, which means inflating in the terms that I've defined before, we get all the isomers of some larger molecular formula. And this phenomenon really resembles what we've shown for polyominoes. So this raises the question for which lattices this phenomenon exists. For which lattices we have this bijection between sets of minimal perimeter lattice animals. And this brings me to our main result. And the main result is as follows. If we'll have these conditions satisfied, we have 3 conditions, and then we have a bijection between sets of minimal perimeter lattice animals for these lattices who satisfy these conditions. The first condition is that the minimal perimeter size should be monotonically increasing. And this is pretty trivial, but we can't prove it for any imaginary lattice that we can imagine, so we require it. The second condition, which is the hardest requirement, we require that the size of the perimeter of minimal perimeter lattice animals will be equal to the border plus some constant. And this is the hardest requirement, usually. And third, the deflation of a minimal perimeter lattice animal should create a valid minimal perimeter lattice, a valid lattice animal. I don't know if it is minimal or not. And what do we mean by valid? Valid means that it should be connected. Okay, so we have these 3 conditions, and now assume that we have a lattice that satisfies these conditions. I'll show that it makes this lattice have this bijection between sets of minimal perimeter lattice animals. So the proof in general terms would be as follows. We want to show a bijection between these sets. So we want to show that if I inflate a minimal perimeter lattice animal, it creates a new unique minimal perimeter lattice animal. And on the second direction, I want to show that if I deflate a minimal perimeter lattice animal, I also get a minimal perimeter lattice animal, but this is not for every size, only for these sizes which are obtained by inflation of some smaller size. And this is what I'm going to show. I'm not going to get into too much details due to time restrictions. So for the first direction, we have a minimal perimeter animal, lattice animal Q, and we want to show that the inflation of it is a minimal perimeter lattice animal as well. How do we show it? Again, I won't go into details, but we'll assume that the inflation of Q is not a minimal perimeter lattice animal, and then we get that there exists some Q prime for which it have the exact same area as the inflation of Q, but its perimeter is smaller. And then using some calculations using condition number 2, we get that the deflated version of Q prime is greater than Q, but its perimeter is smaller. And this contradicts condition number 1, which says that the minimal perimeter size should be monotonically increasing. So this is the first direction, and waving the first direction. And for the second direction, this is the result, essentially. We say that if we take a minimal perimeter poly-X, for example, and inflate it, we get another minimal perimeter poly-X. And for the second direction, we want to show that if we have a minimal perimeter lattice animal, which belongs to the set of n plus epsilon n, where epsilon n is the minimal perimeter of size n, which means that if we take a minimal perimeter lattice animal of size n and inflate it, we get a minimal perimeter of size epsilon n, n plus epsilon n. Then if we deflate it, I want to show that we get a minimal perimeter lattice animal of size n. And again, I won't go into too much details, but if we take this poly-X and deflate it, we can show that we will get exactly something of size n. This is using condition 2 from our theorem. And this new lattice animal of size n will have exactly epsilon n cells on the perimeter, so it is a minimal perimeter lattice animal, and this is exactly what we wanted to show. I'm not talking about that. We have to show also that if we take two different minimal perimeter lattice animal and deflate them, we get two different minimal perimeter lattice animal as well, but we can also show this. So these are the two directions of the bijection, nothing too complicated. So we have these three conditions for lattices, and in lattices that satisfy them, we have this bijection between sets of minimal perimeter lattice animals. But what lattices satisfies them? So I'll start with poly-X's. So for poly-X's, we wanted to show first that the minimal perimeter size is monotonically increasing. This has already been shown in 2008 by Ben-Shachar and Brookstein. And condition 3, we want to show that the deflation of a minimal perimeter poly-X is still connected. It is easy to see. I won't touch the proof in here. You can see in the paper. But the second condition, I've said that it is the hardest one. We want to show that the perimeter of a minimal perimeter lattice animal is equal to the border plus C for some constant C. How can we show this? So what we have done is taken all the cells of a minimal perimeter lattice animal, and in this case poly-X's, and classify them according to their surrounding cells. For example, if we have one cell and then 5 empty cells, this is this pattern, and we can rotate this pattern. And if we have one cell, then one empty cell, one cell, and then 3 empty cells, this is this pattern. And we can classify each cell into one of these patterns. And what we can show is that if we count how many cells of each pattern we have, we get that the perimeter is equal to the border plus this function of the patterns. What can we do with this pattern? Well, it appears that for poly-X's, this pattern is equal to 6 for minimal perimeter poly-X's. It is always equal to 6. And this is great. This is what we wanted to show, that the perimeter is equal to the border plus 6. And by the way, for polyominoes, it is 4. This is only logical. So we have shown all the 3 conditions, and we can see that there is a bijection between sets of minimal perimeter polyhexes. These are all the minimal perimeter polyhexes of size 9, and in the second row, all the minimal perimeter polyhexes of size 23. And this is it for polyhexes, and we've proven this long-known phenomenon for chemists that the number of isomers of these benzoyl hydrocarbons behave as they have seen. So this is it for polyhexes. For polyamides, the situation is a little bit more complicated. If we take a polyamide, you can see that the perimeter is jaggy in some ways, and it creates, if inflated, a jaggy polyamide, and you can guess that it is not a minimal perimeter polyamide, and indeed it is not. We have a polyamide of the same size with a smaller perimeter. So this phenomenon doesn't hold for polyamides, but maybe we can fix it in some way, and it appears that we can. How can we fix it? If we consider the perimeter to not be only cells adjacent to the polyamide, but also cells who share a vertex with the polyamide, like this cell, then the inflation is smoother. And indeed, this phenomenon exists, that if we inflate minimal perimeter polyamides in this scenario, we get all the minimal perimeter polyamides of some greater size. So this is for polyamides. But there is one lattice that we don't know the answer for, and these are higher dimension polycubes. We know that the second condition of our theorem doesn't hold for polycubes, but it doesn't mean that there isn't a bijection for polycubes. It does only mean that we can't prove it using our theorem. But what can we say about it nevertheless? We know that for the small sizes of polycubes that we can look at all the polycubes, we can only go to low teens sizes. For these sizes, we know that the phenomenon does exist, but we are not sure if it exists in bigger sizes. It remains an open question, and this is still an open question. And lastly, the last thing I want to talk about is how many minimal perimeter polyhexes or polyominoes are there. I won't talk about the details, but we have an efficient algorithm to count them, and this is the result. And why do I show you this? Because first of all, it is a pretty graph, but it raises a lot of questions. It has all these patterns in the graph, and the question is, are these patterns a phenomenon raised from our theorem, which means that if we inflate, we get some point which is identical in height, and then if we take these copies of columns, we will always get some patterns like that. Or is there any other meaning behind these patterns that we can't tell about? So these are the count of how many minimal perimeter polyhexes are there for a given size, but we don't know too much about these patterns beside that they exist. And I'll finish with remind you all the questions that I've raised. Is there a bijection between sets of minimal perimeter polycubes? We don't know. Are all the conditions necessary? Maybe the second condition isn't necessary and there is some way around it, and then we will be able to prove it for polycubes. And lastly, what are these patterns in this graph? That's it. Thank you.